Good day. For those of you who don't know us, we're the instructional staff for ECE 150. Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to describe the insertion sort algorithm and implement it. Now, in this lesson, we will describe the algorithm first of just inserting a new entry into a sorted array. We will consider the implementation of this algorithm, and then we will ensure that our implementation works with sufficient testing. Using this function, we will then implement a function that implements the insertion sort algorithm. All right, let's start. Now, suppose that you have an array of capacity 10 and the first 9 entries are already sorted. So for example, here we have an array with 10 entries, and you'll observe that the first 9 entries are sorted, but the last entry, 6, is out of place. Question: how could you convert this into a sorted list? Well, the obvious answer is, of course, to take 6 and place it between 5 and 8. But how could we do this algorithmically? Well, one possibility would be assign the last entry there to a local temporary variable. So now we're storing 6 in some temporary variable. The next step would be, starting from the back, copy to the right any entries that are greater than this temporary variable. That is, copy any value over that is greater than 6. So doing so, we move 23, 20, 17, 13, 12, 8, and now we're done because 5 is less than or equal to 6. If that third entry contains 6, we wouldn't have to move it. At this point, we copy that value stored in the temporary variable back into that now available opening. So here we now have a sorted list of capacity 10. Can we implement this as a function? So the function declaration would be as follows. We would be inserting into an array, and the capacity of the array is given. The assumption is that the entry in the last location is not in place. All right, so let's think about what operations we performed here to get the array with 10 entries where the last entry is out of place into an array that is sorted. That is, how did we insert 6 into the array? Well, we stored that last entry in a temporary variable. Let's call that value. Now, that creates a hole in the last location. So there's a hole at index 9. And then we checked, is what is at index 8 greater than the value? Yes, it is. If it is, then we copied over or assigned entry 9 the value stored in entry 8. Okay, so that moved 23 over by 1. Then we looked if array 7 was greater than the value, and if so, we moved the value at index 7 into the index 8 location. We would have proceeded on to do so until we got to the hole being in index 3. At this point, we would have checked and said, the array entry 2 is not greater than the value, and then we assigned index 3 the temporary variable. So we have a variable k that seems to start at capacity -1, 9. because the capacity of this array is actually 10. What is our test? Our test is the previous entry greater than the stored value? If it is, then we assign the entry k the value in the previous entry. At the end, if the condition is not met, we assign to entry k the value that was temporarily stored. Okay, that sounds like something we can implement as a function. All right, so here is our implementation of the function we just described. First of all, we're going to make sure that the array is sorted. So we're going to assert that the first capacity minus 1 entries of the array are indeed sorted, and you'll recall that is sorted returns the second argument if the array is sorted, and if the array is not sorted, it will return the first index of an entry that is less than the previous entry. So if the array is not sorted, it will return a value between 1 and the second entry minus 1. All right, let's temporarily store the entry at the end of the array. And now we have a for loop. So the loop variable k starts at capacity minus 1, which is what we saw in the last screen. We continue iterating so long as the previous entry is greater than the value, and with every single step we decrement the value of k. If the condition is met, we will assign the entry at index k the value in the previous entry. If, however, the condition is not met, the loop terminates, and we assign to entry k the value that was temporarily stored. Now, some of you may have noticed a mistake here. For those of you who did not, see whether or not you can determine what that error is before we carry on. All right, here is a program that we can author to test this function. Here we have a main function, we have the isSorted function, and we have our insert function. All right, now here I have declared an array of capacity 10 that has those 10 values in it, and then I call insert on that data with the second entry being capacity. Okay, I will then check to ensure that the array is indeed sorted. Now, in theory, this should print 10 to the screen, as the array should indeed be sorted. All right, let us compile the program containing this function. Well, unfortunately, instead of compiling, we get a compilation error. It specifically says on a specific line that k was not declared in this scope. Now, that line is the assigning of array entry k the value of the local variable value. Okay, so what happened here? You will recall that if a loop variable is declared in the first statement of a for loop, then the scope of that variable is restricted to the loop, including its body. So consequently, the last statement there, where array entry k is assigned value, that statement has k no longer being in scope. Okay, not a problem. We can fix this. I'm going to fix this as follows. First, I will declare k to be a local variable, and I'm going to just initialize it with the default value. Now, in the for loop, I'm going to assign k the value capacity minus 1. And so now, with the first iteration of the loop, k will have the value capacity minus 1, and then that value will continue to drop. However, the positive point here is once the for loop finishes, the variable k and the value it holds will still be in scope. So we can execute that last statement, which assigns array entry k the appropriate value. Now, interestingly enough, I could have approached this as follows instead. I could have just declared k to be a local variable here and initialized it with capacity minus 1. You'll notice here I have a for loop that has a blank initialization statement. Essentially, this for loop has no initialization component. Now, why am I choosing the previous version? Mostly because at this point, a programmer reading this is going to be a little bit annoyed. For, after all, the programmer will have to figure out, oh, wait a second, what is the loop? It seems that k is a loop variable, and then the programmer would have to read back up and find the declaration of k to find its initial value. So my personal preference is that this is not the correct way to ensure that k remains in scope even after the for loop ends. But that's personal preference. All right, so now when we run our test program, it compiles and the output is as desired. Is sorted returns the value of capacity, indicating that the array is sorted. Now, we should also test this when the last entry is already greater than the last entry of the array. So here, I'm going to have the exact same test, but instead the last entry is greater than the second last. So in essence, I'm trying to insert the last entry into an array when that entry is already in the correct location. Okay. Fortunately, when this compiles and executed, it works as expected. Let's try the opposite. Let's try inserting a value into a sorted list where that value should come first. So here, -9 should appear in the end before the value -3. All right, so in theory, we should be able to run this, and oh, we get a segmentation fault or core dump. Okay, what's happening here? So what might be going on here? Well, we're going all the way back to the start of the array, so let's see what happens when k is equal to 1. Now, when k is equal to 1, the condition is array entry 0 greater than the value? If so, then in the body we assign array entry 1 the value stored in array entry 0. We then decrement k, so now k is equal to 0. What is the test? The test is array entry 0 minus 1 or array entry -1 greater than value? Now wait a second. 0 minus 1. You'll recall that the array entries are unsigned, and therefore array entry -1 will actually be array entry the largest possible value that can be stored in an unsigned size t variable. This is a problem. Thus, we should stop looping if k is equal to 0. All right, if we are to halt if k is equal to 0, then we should keep iterating if k is greater than 0. So we will continue iterating if k is greater than 0 and array entry k minus 1 is greater than the value. Now, notice that this condition actually relies on something we learned previously, short-circuit evaluation of logical operators. So, if the first condition evaluates to false, then the second condition is not even tested. So, given condition 1 logical and condition 2, if condition 1 evaluates to false, the second is not even tested. The entire expression just immediately evaluates to false. And the reason for that is false and anything must be false. False and true is false, false and false is false. So it doesn't matter what the second operand evaluates to. So C++ does not even try to evaluate it. So if k is equal to 0, k greater than 0 evaluates to false. Therefore, we do not test if array entry 0 minus 1 is greater than value. Okay. Now that we've implemented this insert function, we're actually going to use this insert function in our implementation of the insertion sort algorithm. How does the insertion sort algorithm run? Well, here is an array of capacity 10 that is completely unsorted. Now, that first entry in the array is itself a sorted array of capacity 1. However, if we now consider the first two entries, we see that while the first entry is a sorted array, the second entry is out of place. Can we insert 35 into the previous array of capacity 1 that is sorted? Well, yes, we can. We can just call insert on this array with the second argument 2. What that will do is it will put 32 into the index 0 location, and it would have moved 16 into the index 1 location. All right. So now here I have an array of capacity 3 where the first two entries are sorted, and, well, I'm not sure about 15. Well, it happens that 15 is already in the correct location, but just in case it wasn't, I could put it into the correct location by calling insert on this array with the second argument 3. So now the first 3 entries are sorted, and now the first 4 entries form an array of capacity 4 where the first 3 entries are sorted and the last entry is out of place. So we'd like to insert 9 into the correct location, and we do so by calling insert on that array with a second argument of 4. That will put 9 in its correct location. We could then again look at the first 5 entries and note that the first 4 entries are sorted and the last or fourth entry at index 4 has to be still inserted. Well, this is actually the insertion sort algorithm, and we would continue to do this until we have finally placed the last entry into its appropriate location. Thus, at this point, this is about the easiest algorithm we could write. Thus, here's a very simple implementation of the insertion sort algorithm. All we have here is a for loop. And in this for loop, the loop variable k is initialized with the value 2, and it keeps iterating as long as k is less than or equal to the capacity. So if the capacity was 10, this would then execute insert array 2, then insert array 3, then insert array 4, all the way up until insert array 10. That last instruction would then place the last entry into the previously sorted array of 9 entries. So at the end of this for loop, the array will be sorted. we have an assertion at the bottom just to make sure that the array is indeed sorted. Now, one thing you'll notice also is that this implementation does work if the capacity is 0 or 1. If the capacity is 0 or 1, the for loop simply does not execute at all, and everything is still good. Now, note that in our main function, so in our program, our testing was a simple check to make sure that the array, when it was returned, was actually sorted. Is that really sufficient? Suppose we had an error in our code that took the first array here, and instead of correctly sorting it, it simply replicated that first entry 9 additional times. Well, technically, this second array is sorted, but it's not the first array being sorted. Consequently, our testing should actually compare the resulting array with what we actually expect the assorted array to be. But that's just a comment, and you should take that into account. Now, what was the purpose of authoring the insert function? After all, if you go online, you will find that almost all implementations of insertion sort accomplish everything in one function. Indeed, with a few tweaks and variations, if we combined the two functions we authored above, being insertion sort and insert, then the following is exactly what we would get. It would be one function with 2 nested for loops. So why didn't we just do this in the first place? Well, the issue is now we're trying to do 2 things at once. We're trying to get the insertion part correct, as well as we're trying to do sorting at the same time. And it's not possible to test one without testing the other. In our case, however, when we implemented the insert function first, we tested it thoroughly. Once we knew that the insert function was working correctly, the implementation of the insertion sort algorithm became trivial. So again, we are breaking up the tasks. We are factoring out one aspect of the insertion sort and implementing it as a separate function. We then tested that function, at least within the scope of this talk, and once we knew it was working, or at least we're reasonably assured it was working, then and only then did we bother to write the insertion sort algorithm. So following this topic, you now know how to implement the insertion of a new entry into a sorted array. And in doing so, we reviewed the concept of the scope of loop variables. You also now understand how to test a function to ensure it works correctly, and in doing so, we reviewed the concept of short-circuit evaluation in C++. You also know how to implement the insertion sort algorithm, and you can implement this using the insert function we authored. You also saw that it's probably more necessary to be rigorous in our testing than we were, but that's a project you can do on your own time. Finally, hopefully you can appreciate the idea now of breaking a larger problem into simpler problems, where those solutions to the simpler problems can be combined to make solving the larger problem much more easy. Specifically, we looked at the standard implementation of the insertion sort algorithm in C++, and again, if we tried to do it all at once, we probably would have had much more difficulty getting all of the bugs because we were trying to do 2 things at once. By solving the simpler problem first and testing it, the general problem became much easier. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!